let's recap what we did in the first two weeks. Okay, so again in a slightly different context I will recap. So the workhorse in chemical engineering are continuous flow reactors or continuous flow systems. This could even be distillation columns. Okay, chemists, for example, or in chemistry lab, we would have done a distillation experiment where you would have distillation one particular beaker, we heat it up and then we get the light component that comes out, vaporizes, and then we condense those vapors and that forms our light component. That is not how most of the distillation columns work in the industry. The distillation columns, for example, will be very large towers and you will have feed coming in here. Okay, and at the bottom you will have the last boiling component, and at the top you will have the lightest component or the easiest boiling component. Okay, so this is how a simplest of distillation column will be run. There might be packed bed, there might be plate columns and so on. Okay, there are various different types of distillation column. Now, some of the distillation columns may not actually have just two, one at the bottom and one at the top. They might actually have multiple outlet streams as well. Okay, and typical example is crude oil distillation. Okay, the topmost fraction is are the gases. So typically the liquefied petroleum gas LPG comes as one of the topmost components. Thereafter you have gasoline or the petrol fraction, the diesel fraction, kerosene fraction, the heavy fraction, which some of which goes into aviation fuel, and then the heavy oil which is used either as lubricant or a component of that goes into marine fuel. So the fuel that is used in large ships, right. So all of this will come from one distillation column. The distillation column might be 10 stories tall. Okay. Likewise, when we look at reactors, lot of reactors, especially if it is gas phase or liquid phase system, lot of reactors will be flow reactors, which is, we gave that analogy at the flow reactor. Now the model for the flow reactors by doing in minus out and so on was okay. So this is what we got as our model, and if this is not transient, this is steady state, we are going to get dfk by dv equal to rk, or d of qck by dv, and if q was constant, we will be able to rewrite it like this, only if q was constant, right, and this becomes dc by d tau equal to rk. Okay. Now this was where, so I started off with analogy, now I am just starting off with an equation, and this I had given you analogy of, see a batch reactor, you have dck by dt equal to rkv, no sorry rk, this is again constant volume batch reactor, right. So this is the analogy that we gave, but now if we put this batch reactor on a conveyor belt, what changes with time in this reactor can be seen to change with tau as we move along the conveyor belt. Okay. Keep in mind that this is an analogy, and analogy does not mean reality. What I mean by that is, analogy is something that you use in order to understand something. It is not something that you would want to use necessarily to solve something in future. Okay. When it comes to solving problems and so on, you are going to use the mathematical concepts that we are learning. Avoid using analogy, because again there are certain assumptions that have gone into the analogy. As soon as those assumptions are not met, what you get is something that is incorrect. So, do not use this analogy to solve any problem. Okay. Just use analogy to think about the physical situation that works. And again we use this same analogy to give ourselves an idea why we have said that infinite number of CSTRs in series is equivalent to a plug flow reactor. Okay. So, here we have talked about continuous flow reactors, tubular or plug or plate type of systems. The other continuous flow reactor is basically a well mixed reactor, CSTR, continuous stirred tank reactor, and PFR, plug flow reactor. Okay. So, in CSTR you have inlet and outlet, and the assumption is that whatever you see at any location within the CSTR has the same value at the exit of the CSTR as well. So, everything is well mixed within the reactor. Okay. And there is a whole bunch of reactors that are physically used that do not follow CSTR or PFR principles, but some of them can be reasonably be approximated as CSTRs and PFRs. Okay. And that is the reason why we study these two reactors quite a lot. Okay. Then we talked about stoichiometry and reaction rate, and you can take any reaction that you are interested in. So, let us say methane steam reforming. So, the methane steam reforming is a reaction that gives CO plus 3H2. Okay. So, the stoichiometric coefficient is -1, -1, +1, +3. Okay. That is the stoichiometric coefficient of various species undergoing that reaction. If there was an inert or there was another species not participating in the reaction, the stoichiometric coefficient for those two species would be 0. Okay. You might also have additional reaction, the CO that is formed by that reaction might undergo a water gas shifts reaction to form CO2 plus H2, and if that is the case, then for CH4, the stoichiometric coefficient is 0, for H2O the stoichiometric coefficient is -1, for CO the stoichiometric coefficient is -1, for H2 the stoichiometric coefficient is +1, for CO2 the stoichiometric coefficient is +1, and for N2 the stoichiometric coefficient is 0. Okay. And this is how you will get the stoichiometric coefficients. Okay. And then you can form the stoichiometric matrix, which has NS number of species. So, your species might be CH4, H2O, CO2 and so on. Okay. Now, reaction rate, one statement I made is that the IUPAC definition of reaction rate for this course, or for that matter in CRE course also, we have rather than thinking of that as a definition of reaction rate, we will think of that as just an outcome of a balance on a constant volume batch reactor. Okay. So, this is how we use reaction rate. Okay. One way is, if it is given, it will be given in terms of a constitutive relationship R1 equal to K1 PH2O2 to the power alpha, PCH4 to the power beta, and it might have a denominator or something like that. Okay. So, if it's given something like this, you substitute the values of concentration or pressure inside that expression, substitute the value of temperature inside that expression and compute the rate of that particular reaction. Okay. Other way is to obtain from experiments. Okay. So, we will run certain experiments, and this is something I will come to the class, to the next class, we will, or the next class perhaps, we will run certain experiments in order to get the rate laws. We will run the experiments to compute the value of K1, to compute the value of alpha and compute the value of beta. So, here the idea is to compute K1, alpha and beta from the expressions. Okay. And the third one, and that is something that I will come to 2 weeks from now, is to look at the relationship between rate and mechanism. Okay. That is basically your module 3 and 4. This is module 2 entire course. Okay. That is how we will use it. So, this is just looking a little bit ahead. Okay. Then we talked about the overall balance equations, and the overall balance equations we looked at for well mixed, okay, and depending on that situation, this could be RK dash S, where S is surface area, SA, or RK double dash rho B, where RK double dash is given in terms of moles per kg per time. Okay. So, these might be the other two cases. We will use these cases after basically week 5 of this course. Okay. Now, Fk in, Fk out, what they are, how they are related to various processes or various measurable quantities depend on whether it is liquid, gas, multiphase flows and so on. Okay. It is always Q multiplied by C, but Q multiplied by C may not be an easy term to calculate sometimes, or may be an easy term to calculate some other times. So, which form that you use the balance equation really depends on the situation. In your assignments, in your problem sheets, in the problems that you solve in a course, all that information is almost directly given to you. You do not have to figure out what to use. But in research, sometimes you will need to figure out how do I substitute our F value and so on. Okay. And depending on how you substitute it, things can be very simple or very complex. The math can become very simple or very complex. Okay. Plug. Okay. So, that is the recap of what we have done in the last 2 weeks. Okay. So now that leads me to the next thing is RJ is basically rate of reaction, the rate of progress of a reaction, and I have made an example later on in this particular module where we will actually solve a CSTR or a PFR problem, so that you will directly see how we can solve that. Okay, we'll probably be able to do it in the next class, tomorrow's class. Okay. So the reading material, your textbook from and Bischoff, chapters 1 and 2, and from Davis and Davis chapters 2 and 3 and appendix A. Whichever book you want to use, you may. I follow both the books, but mostly it's based on my experiences, so both that information is used, and some of the information will be there from Davis and Davis chapter 1. So if you have just time to read one book, I would recommend doing Davis and Davis chapters 1 to 3, especially if you do not have a strong CRE background. If you are reasonably confident of your CRE background, jump over to Froment and Bischoff. Okay, Froment and Bischoff is a postgraduate text, so it would be a little bit tougher to read than Davis and Davis. Davis and Davis is a cusp level text. It's good for people who have done a CRE course, but also it refreshes all the concept from kinetics aspects. Okay, so whichever one you are comfortable with, you can. In later chapters, we will end up using Froment and Bischoff a bit more than Davis and Davis. Okay, but again, the notes that I have are based on our experiences teaching and doing research, because as a postgrad course, it deviates somewhat from the textbooks. It does not follow. So if you are going to ask which chapter of the textbook or where exactly in the textbook this particular material is, I will not pinpoint, and I would not encourage those questions either, because this is a PG level course. However, at various points I will try to ensure that looking at these textbooks and these chapters, you will be able to directly understand what we are doing and follow closely what we are doing. Okay, so what does the reaction rate mean? Okay, this is again this particular thing. I didn't have this a couple of years back, but then there were a lot of questions about reaction rate, and especially in the context of semi-batch reactor. So if you look at, I think your problem 4 in your assignment is a semi-batch reactor problem, and so if you're going to use something like dC by dt, because it's a constant volume semi-batch reactor. No, it can't be a constant volume, sorry, scratch that. If you use dC by dt or 1 by V dN by dt equal to R, that particular expression, you will find that what you get is incorrect. Okay, we will come to that particular problem after your first assignment is done, but let's look at what does rate of reaction mean. Okay, let's say there are two types of balls, red color and purple color balls. Okay, and what is happening is there is a transformation of red color balls and purple color balls taking place. Okay, so let's say that this is the snapshot at time t, and this is a snapshot at time t plus delta t. Okay, so now there are all of these balls that are present. Okay, to these balls between t to t plus delta t, you have 2 purple balls that got added, okay, and 3 red balls that got added. Okay, 1 purple ball that got removed and 2 red balls that got removed. Okay, so you had +1 of red and +1 of purple happening because of flow. This is not happening because of reaction, this is happening purely because of the number of balls coming in minus number of balls going out. Okay, now certain balls of purple disappear and certain balls of red disappear. okay. And let us say what is happening over here is that these are the purple balls that have been converted into red, okay. So these two balls which were previously purple have become red, okay, but these balls have gotten added because of the net flow, okay. So if you see both these, so the locations have tried to keep the same, right. So all of these balls are remaining in that same location. This purple ball has switched to this red, this purple ball has switched to this red, okay. Now if you look at dn red by dt, okay, how do you do dn red? See the number of red balls at t plus delta t, subtract the number of red balls at t. How many new red balls are there? 3. 1 came in because of flow, 2 came in because of conversion, okay. So dn by dt is 3, but rate of reaction is actually just 2. 2 are added, 2 red balls are added because of conversion of purple to red. 3 red balls are added because of in minus out plus conversion, okay. Now let us look at purple, okay. 1 purple ball got added got added because of net flow, 2 purple balls got removed because of reaction, okay. So if we were to do d by dt of n purple, okay, this one is going to be 3 right. This accounts for flow, this accounts for reaction. If we were to blindly use the definition, IUPAC definition, which is there for constant volume batch non-flow reaction system under isothermal conditions, if we were to blindly use it, what we are going to get? dn red by dt is plus 3, dn purple by dt is minus 1, and then oh, but the reaction is purple goes to red, 1 mole of purple goes to red, what's happening over here? And we will get confused. What's happening over here is very simple. There is things that are coming in because of flow, there are things that are changing because of reaction, and only the things that are changing because of reaction go into the R term, okay. So coming back to how are you going to use this? How you are going to use this is in one of these 3 ways. If you want to calculate the design problem or conversion problem and so on, you substitute the value of concentration or partial pressure or mole fractions or whatever else it might be into the constitutive relationship. Constitutive relationship is R equal to some bunch of terms on the right hand side. If everything on the right hand side is known, you plug it in, you get the value of R. To obtain the kinetics, you collect the data, okay, and you put the data in, you know your concentrations, you know your rate R, or you calculate your rate, but you do not know your K or activation energy or alpha beta. So you compute K or activation energy or alpha beta from the data. So your right hand side is known, the variables in the left hand side are known, the parameters are not known, and you estimate the parameters by curve fitting, y equal to mx plus c type of curves you can fit. Okay, that is the second type of problem. Third type of problem is that given bunch of elementary reactions, and we will come to that in a few minutes, given a bunch of elementary reactions, can you figure out what the net reaction rate will look like, or given the net reaction rate, can you figure out what are the sub steps that are taking place in the overall system. We will do that for gas phase, liquid phase reactions, for enzymatic reactions and catalytic reactions in module 3 and module 4. Okay. Okay. So, what is chemical kinetics? Okay. Chemical kinetics has various aspects to it. Okay. One is the form of the rate law. What are the typical forms of rate laws have you known so far? We have talked about that already. Sorry? How is the temperature dependence? Arrhenius. Does the reaction rate depend on pressure? Sometimes. In some cases it does, some cases it doesn't. What are those some cases where it doesn't? Liquid. Okay. Again, strictly speaking it's not true, but as far as our course is concerned, it is true. I can always again give examples where liquid phase reaction rates depend on pressure. What will be an example where reaction rate depends on pressure? Gas phase. Okay. If gas phase reaction rate depends on pressure, does it mean it does not depend on concentration? No, because let us say PV equal to nRT, okay, or P equal to CRT, or PK equal to CKRT. So, partial pressure and concentration can be interconvertible. So, when do you use partial pressure, when do you use concentration? Depends on convenience, or it depends on the history. So, for example, in my group we are very likely to use partial pressures, okay. Some other groups they are likely to use concentrations. Why? That is historically we have been in the area where people tend to use partial pressures. So, it is more convenient for us to use partial pressures in gas phase reaction, concentrations in liquid phase reactions. Okay. Someone who works in multi-phase systems, for example, Professor Swapna's group or Professor Himanshu's group, they are likely to use concentration because they will use concentration both in gas and liquid. Okay. So, there isn't one answer, but the idea is that the rate law depends on how many moles of the species are there per unit volume, calculated in terms of concentration, mole fractions or partial pressures, and it also depends on temperature. Okay. So, what is the rate of a chemical reaction? Does it refer to the speed of progress of a reaction? Moles converted per unit time. Yeah. So, remember that it is moles converted per unit time, often per unit volume or per unit surface area or per unit mass. Okay. So, reaction rate is moles per volume per time. But you already have a counter case of where we did not use this example, this definition, right? The Lotka-Volterra model, the predator-prey model, where the rate of reaction, again it is not reaction, but the rate of reaction was in terms of numbers per unit time, not numbers per unit volume per unit time, but numbers per unit time. So, yes, for the most part, for 90% of the cases that we will do in this course, we are going to use moles per volume per time or moles per surface area per time in case of surface catalyzed reaction, or mole per kg per time in case of heterogeneous catalyzed reactions. That could be surface catalyzed or enzyme catalyzed or for example biological reactions, okay, but they will be in terms of moles per volume or per time or surface area or per kg per time, okay. Reaction mechanisms is basically refers to the way in which the reaction proceeds in terms of intermediates and so on and so forth, okay. The examples that we are going to look at will be enzymatic reactions, okay. So you have a substrate and you have an enzyme. So let us say the substrate looks like this, okay. We love spheres, so we will represent anything as a sphere, okay, and there is an enzyme. So that enzyme can, and you have seen this in terms of you know, the unfortunate COVID, right, spike proteins, okay, and spike protein receptors. What that means is that there is a particular structure of that of the receptors on human cells, and what the virus did was it made proteins on its surface that are complementary to this particular receptor. Now these receptors has some kinds of bonding that are stronger than van der Waals forces, some kind of hydrogen bonding or something else, and through those bondings, once this particular spike protein comes in touch with the receptor, it binds strong enough that it cannot be knocked off by typical processes that happen in human body, okay. Why does, for example, fever increase? Is because to create situations or within the body such that some of these bonds are broken either between receptors and proteins or within a cell, okay. It kinds of spurs our defense mechanism to act against it, okay. So this is an example where the same concept was exploited by the virus in order to infect us, okay. So what happens after S plus E is it will form a complex, it is SE actually, this might look something like this, let us say it could be an oval also, okay, and thereafter it can undergo a reaction and it will form PE where it is product and enzyme, and then the enzyme will separate and go back, okay. So there will be a small amount of enzyme that keeps reacting over and over again with the substrate and cause a lot of reaction, okay. So S plus E giving SE, SE giving P plus E, okay. That the earliest was called Michaelis-Menten, okay, and the rate law that emerges from Michaelis-Menten is of the form of this form, okay. How we will get to this and all that we will talk about in the next module, in module 3, okay. So the form of the rate law in this particular example is this form, the mechanism is this, okay, and the rate of chemical reaction can be computed once you know the value of Km and Ks. Alternatively, you can carry out reactions, measure the concentration, measure the rate of reaction and use that data to compute Km and Ks, okay. All of these are the things that we are going to learn over the next 3 weeks, okay. So what are the things that rate depends on, rate of reaction depends on? Temperature, pressure, concentration, okay. Concentration of reactants, it could also depend on concentration of products as well. So in Michaelis-Menten case, something called product inhibition is where presence of product or product will complex with your enzyme, and there will be product inhibition. Okay. So, it will depend on concentration of reactants products, it could depend on concentration of other species. Gas phase reactions, for example combustion reactions, it might also depend on general concentration of third body species. That means anything that can collide with hydrogen or anything that can collide with oxygen will result in formation of an oxygen free radical, provided that collision is energetic enough. Okay. So, those are the type of reactions you have probably not encountered in your undergraduate. Maybe some chemists have, maybe they have not. Okay. Then there is a strong dependence of temperature, which you noted. This dependence of temperatures is incorporated into what is called as rate constant. Okay, through, as you all said, Arrhenius law. Okay. So, there is a function of concentrations, there is a function of temperature. The function of temperature we represent as K, okay, and the general expression R is in terms of F of T comma C or F of T comma P. Okay. This K has Arrhenius law, which is say A naught e to the power minus E by RT, where E is the activation energy. Okay. The extended Arrhenius form also has T to the power beta term. Okay. This comes in because, and this is the last statement that I will make today, and we will pick this up tomorrow. Okay. You remember this diagram? What is this? Energy diagram. Where is activation energy? Okay. Not just activation energy, this is true also for an entropy diagram or for a free energy diagram. If we were to do free energy instead of this, this is represented as delta G hash. Okay. Now, delta G has enthalpic component and entropic component, right. So, this is EA okay. This particular component gives rise to this part, okay, and entropy need not always be constant with temperature, entropy could change with temperature, and therefore you have an extended Arrhenius form in the form of T to the power beta. You use extended Arrhenius form when you need to relate your pre-exponential terms with thermodynamics. You use the Arrhenius form without T to the power beta, which is again 85%, 80% of the cases today. You use that when your A naught is obtained from experiment. Okay. So, if you are building a mechanism ground up from molecular or quantum level understanding, there would very likely be the T to the power beta term. If not, there will not be T to the power beta term. If not is the 80% of the cases. Okay. Just 15 years back, if not, were 95% of the cases. Okay. So, your textbooks were written more than 10-15 years back, so they do not necessarily have any kind of emphasis on this. We are also not going to emphasize too much on this, though that is advanced level courses, but just to give you an idea, there is a lot more to the things that we have learned so far beyond the most basic stuff that we are teaching. Okay. Alright, so come to the end of this lecture, and any questions? Ethane, yeah. So, don't please expect that there might be minor typos in assignments. Okay, assignments sometimes we end up doing very quickly, so there might be typos. I usually solve the assignments before putting it on there, but I don't solve the assignment right till the end. Exams on the other hand, we are a lot more careful. It's I try to solve it at least in 2 different ways and so on. So like again, it's a human exercise, so there is likely to be some error. So expect errors, and with assignments and so on, you can always ask me, but you can use your judgment as well. So in the example, we have assignment, we have ethane dehydrogenation, and somewhere I had methane. That might have just been while typing, because we work a lot with methane, automatically my hand went to the letter M, or it might be because it's copy pasted from last year, and last year I had a methane based reaction in there. Okay, alright, we will see you in the next class. Thank you.